Hi students, I am Naresh. I am actually teaching chemical kinetics, the chemistry topic for Sri Chaitanya Re-NEET Sankalp 2. So this is a very important physical chemistry topic dealing with the speed with which a reaction can proceed. When thermodynamics can tell whether the reaction can proceed or not, kinetics always tells about the speed with which the reaction proceeds, the factors influencing the rate of the reaction, the mechanism of the reaction. All these things are being studied here. We will try to learn it in a more simpler fashion, make it as simple as possible. Based on the rate or the speed with which a reaction proceeds, we actually study them under three categories. The first category or the class of the reactions is instantaneous or very fast reactions. Ionic reactions are instantaneous. Neutralization reactions involving acid and base. Precipitation reactions come under this category where the reaction gets completed within fraction of a second. Before you find out the rate, the reaction is over. So you cannot find out the rate. The other extreme is very slow reaction. Rusting of iron is such an example. Also, if you try to react hydrogen and oxygen in absence of a catalyst, even after a considerable time, we cannot see a drop of water also forming. It is a very slow reaction. The reactions which are not fast are very slow and whose rates can be measured are called reactions which are moderately slow reactions. That moderately slow reactions are what we are studying today. Then the next point is, what exactly is the rate? Rate in physics we call it as velocity. Rate of reaction is velocity of a reaction. So in physics we call it as dx by dt. Let me change my pen's color, better it will be dx by dt, but we in chemistry generally use dc by dt or dp by dt. So what is it? A change in concentration in given time, sometimes represented like this also. What is the difference is very simple. If there is a finite time, we use delta. If you use infinitesimally small time, we use d. Whatever is the case, change in concentration per unit time. Rate of change of concentration or rate of change of pressure. For gaseous reactions, pressure is considered. For aqueous solutions, concentration is taken. This is how we generally represent an average rate or rate of a reaction. Hence, units of rate will be always mole, liter inverse, time inverse, or minute inverse, or second inverse. Make it a point. Time inverse is more important. It is unlike in electrochemistry or something like that. The rate need not be measured for every second. It can be a minute inverse, it can be a second inverse, or it can be hour inverse, or it can be a day inverse, or a year inverse. Means you can measure the rate per day, per year, per second, per minute, anything. A very important aspect of this particular chapter is, irrespective of the order of the reaction and the nature of the reaction, units of rate will never change. They will be moles per liter per time or pressure units per time. Then the question comes, how to actually study the rate of reaction, what exactly is the meaning of the reaction. If you see here, if you take any reaction where reactants give products, always you know reactants concentration with time decreases exponentially. This decrease in the concentration of the reactants with time is nothing but rate. At the same time, the concentration of the product with time increases. This increase in the concentration of the products with time is nothing but called rate. But once you write, once you draw a graph of rate versus time, never try to do a mistake of writing this way, because rate of a reaction always decreases with time. So these are the three things. Rate of a reaction always decreases with time. What is the reason, sir? Very simple. As time passes, concentration of the reactant goes on decreasing. You know very well, rate depends on concentration of the reacting substance. Once the concentration of the reacting substance decreases, rate always decreases. Then the question is, will rate be a constant sometimes? Yes, a very rare chance is there. A very rare chance is there. A special case is there where rate will be remaining constant with time. This is when order is equal to 0. Such a reaction in which rate does not change with time, rate remains constant, concentration changes of the reactants do not influence rate, is a 0 order. Here order is not equal to 0, whereas here is order is 0. Your question will be, what is order? That will be the that will be studied in the next part. Means we will continue now and proceed. These are the few things that I wanted. And how to write a mathematical expression of rate is what we see. Suppose if you take a simple reaction, A gives B, rate of a reaction is actually represented as minus delta A concentration by delta T is equal to plus delta B concentration by delta T. Here minus does not indicate rate is negative, negative indicates only to say that concentration of the reactant decreases with time. But the question comes, what happens when some coefficients are also being introduced? I mean to say 2A gives B. How to write? Rate is equal to minus half of delta A by delta T is equal to plus delta B by delta T. Make it a point, whatever is the coefficient, it should be written as a reciprocal. What is the meaning of it? I wanted to say, this rate is called rate with respect to rate of the reaction is nothing but rate of reaction is nothing but rate with respect to A or rate with respect to B. Once you say rate of reaction, suppose if one says for this reaction only, rate of reaction is X moles per second, then what is rate with respect to A, rate with respect to B? Rate with respect to A is equal to rate with respect to B is equal to rate of reaction, all will be the same and whose value will be X. So once they say rate of reaction or rate with respect to X or rate with respect to A and rate with respect to B, it should not change because it is equal to average rate. But the point is, if you see we have 2A gives B, then what is the rate at which A is disappearing compared to B? Rate of disappearance is twice the rate of appearance of B. I mean to say, when 2 moles of A are disappearing, 1 mole of B is forming. For every 2 moles of A disappearing, only 1 mole of B is forming, indicating rate of disappearance of A is double that of B. Then how to show it mathematically from the previous equation? Yeah, rate is equal to minus delta A by delta T is equal to delta B by delta T. What you wrote now, this is what we studied, and we studied that minus half of delta A by delta T is always equal to delta B by delta T. In the previous part we wrote it as x moles per second. So rate with respect to A is equal to rate with respect to B is equal to x. But now what is minus delta A by delta T equal to? Take this 2 to this side, which is equal to 2x moles per molar per second. Means what? This minus delta A by delta T is what we call it as rate of disappearance of A. So rate with respect to A is x, but rate of disappearance of A is 2x. So coefficients play a vital role here. Luckily and fortunately for us, B has no coefficients. Therefore, rate with respect to B is also x, rate of appearance of B is also x. Let us take one more example to understand it in a better way. Let us say 2A gives half B. Then people say rate is equal to minus half of delta A by delta T is equal to plus 2 into delta B by delta T. We are writing the coefficients as reciprocals. Rate of reaction, rate with respect to A, rate with respect to B. This is with respect to, this is also with respect to, this is B, this is respect to. But the question is, what is minus delta A by delta T, which is equal to 4 of delta B by delta T? What does it mean? Rate of disappearance of A is this. Rate of appearance or formation of B. Now tell me, rate of disappearance of A is 4 times rate of appearance of B. You can see very clearly, correct. 2 moles of A are disappearing, half mole of B only is coming. So for every 2 moles of A disappearing, only half mole of B is forming. What does it mean? Rate at which A disappears is 4 times rate at which B appears. So be careful in the examination. Are they asking rate with respect to A, with respect to B, with respect to reactant, with respect to product? Are they asking appearance and disappearance? If they ask rate of reaction, average rate with respect to reactant, with respect to product, the value remains the same. Once if they say rate of appearance and disappearance, then the coefficients play a vital role. Also, one more important factor to be considered, in all the numericals that we are doing here, I was using, let us say, moles per second. Sometimes it is very much to be concentrated that I may give you a question in moles per liter per second, I may ask in per minute. So multiplying with 60 or dividing by 60, units play a vital role in kinetics and the numericals that you take up. Please always watch out for the units here. Now you got an idea about rate. Then the question comes, sir, I am just listening about average rate, instantaneous rate, how to differentiate between them, what is the difference? To know that, suppose if you take reactants concentration with the time, you have a reaction like this. Suppose if you take any two time intervals, suppose I took this time interval and I took this time interval. This is C2, this is C1, and this is this is actually T2, this is T1. So what is this? This is called delta C and this is actually called delta T. This delta C by delta T is nothing but called average rate. Average rate you can take anyway. Suppose some other person wanted to tell the average rate here for this particular reaction. Why should they take only the same two time intervals? Someone will take a time interval like this and someone will take. So this particular delta C and this particular delta T can be taken. So average rate is always calculated by taking any two time intervals, and during the time interval what is the change in concentration is this, which is a definite amount of concentration change for finite changes. But sometimes you wanted to find what is the rate at 5th minute, what is the rate in the 10th minute, 15th minute, you wanted to know at a particular instant. Then what to do then? So very simple, the same type of a graph is drawn here, and for this graph you try to actually draw a tangent, and the slope of this tangent actually will give you at this point, let us say this point is a 10th minute. For this particular point at 10th minute, you are finding out at 10th minute, find out the slope. The slope calculated for the tangent that you draw always talks about the instantaneous rate. You have selected this point where the time is 10th minute. You actually you took a slope of that particular tangent. That slope of the tangent will tell you what exactly is the rate of that reaction in 10th minute. Since we are considering at a particular time where the time tends almost equal to 0, we actually use the word dC by dt, d, small d. When you use delta C by delta T, it is generally average rate. When time tends to be 0, then we use dC by dt. dC by dt is called instantaneous rate. Instantaneous rate always can be attained only by drawing a tangent to a graph of concentration versus time for a reactant or for a product. Instantaneous rate is actually very difficult to find out. So many cases it is always better to know average rate. No doubt about it that instantaneous rate always gives you better idea about the rate of a reaction. The question comes then, sir, what are the factors influencing rate of a reaction? To know what are the factors influencing rate of a reaction, I wanted you to understand one important concept called energy profile diagram. Energy profile actually will always give you a correct idea. Suppose an exothermic reaction is there, an endothermic reaction is there. Exothermic reaction, reactants energy will be greater than products energy. Greater than, let me correct this, greater than. Endothermic reaction, energy of the reactants less than that of product. For example, if anybody is giving you a potential energy versus reaction coordinates is being drawn by you, if you see an exothermic, the graph will be looking like this. If you see the same type of wave of endothermic, the graph looks like this. You can see this is the reactant energy, this is the product energy. This is the reactant energy, this is the product energy. This is called energy profile, and a reaction is drawn here. So let me be very clear, if you know this, I will once again draw in more detail. So, this is a very important aspect. Let me concentrate on certain things. I will once again come back to this, the next one. So, I am going into more details of it. I have a exothermic reaction, potential energy versus reaction coordinates. This is reactant, this is product. This corresponds to this energy, this is this energy. This is the energy called threshold energy. What are they? I will tell you once again. This is called EA, this is called EA dash, and this is called delta H. This is for exothermic. So, let me be very clear. What are they? This is the energy of the reactant, this is the energy of the product. A reactant can get converted to product only when it can cross that barrier. The maximum energy that it has to attain is called threshold energy. Then what is the energy that it has? R. What is the energy that it has to attain and achieve to cross the barrier? Is threshold energy. How much less does it have? It has this much of energy it has to achieve. So, what is the extra energy that must be gained by it? EA. This EA is called activation energy. Suppose if this reactant I am taking it as A and this reaction I am taking it as B, means let us say the reaction from A to B. What is the reaction activation energy for the reaction A to B? What does it mean? It means that what is the energy of the reactant A and what is threshold energy? The difference in the energy is nothing but called activation energy. The activation energy of the reactant energy is this one, and this is the threshold energy. EA is the extra energy that it must gain. So, thus the additional amount of energy that must be gained by the reactant molecules to attain threshold energy is called activation energy. So, activation energy is equal to threshold energy minus energy of the reactants. Can I now say, if it is a reversible reaction, what is the activation energy for the reaction B to A? The activation energy is EA dash. What does it mean? If at all B wanted to convert to A, how much energy that it should gain to cross the barrier? It has to gain a energy barrier of EA dash. So, in this case with your common sense, you can very clearly see, assuming if it is a reversible reaction, it is easier to go from A to B because lesser value than B to A. Can I now say that lesser the activation energy, faster is the rate of reaction. Hence, throughout this particular chapter, we use an important word or term called activation energy. Then the question comes, what is delta H, sir? This is the energy of the reactant, this is the energy of the product. Reactant has this much energy, but the product has lesser energy. What happened to the remaining energy? When a reactant is getting converted to product and reactant has a greater energy than product, the remaining energy is lost in the form of heat. That heat liberated in this case is given as delta HR, change in enthalpy, and this delta H is always negative because it is an exothermic reaction. What happens if this reaction is endothermic? So, I am just putting a simple way. Now tell me, is it not the activation energy of the forward reaction? Is it not the activation energy of the backward reaction? Is it not the difference between them called change in enthalpy, delta H? Here delta H is positive because it is endothermic. The most important point that you should always remember is exothermic reaction always has reactants energy greater than product energy. Endothermic reaction always has energy of the reactant lesser than that product energy. Then the graphical representation is the best way to solve any numerical related to activation energy and delta H. To understand this particular concept in a better way, we will try to solve a numerical. They gave you like this. Let me be very clear, activation energy does not have a negative sign. It is always the magnitude that is very important. And they are asking you B to A, what is activation energy that they are asking. Very simple. First, the most important thing is this is an endothermic reaction. So therefore, first we will try to draw a graph that shows that endothermic reaction. Endothermic reaction. Nice. What exactly is the activation energy for forward reaction A to B? This is given to be 50. Do you agree? This is the energy that is required for A to B. What did they give other than that? Oh, this value that they gave is actually given to be 20. Very nice. Activation energy for forward reaction 50. Endothermic reaction energy absorbed is 20. Then the question is, what is EA dash? So therefore, EA dash is equal to 50 minus 20, which is equal to 30 kilojoules per mole. Did you understand this question, all of you? Suppose if they give A to B, delta H is equal to minus 90 kilojoules per mole. B to A, EA is how much? If A to B, EA is less than, let us say 70 kilojoules per mole. First thing that you should understand, this is an exothermic reaction. Exothermic reaction, energy of the reactant greater than the product. So this is exothermic. What is the delta H value given? Oh, 90. This is the delta H value. What is the EA value given? Oh, this is 70. Very nice. What is this value equal to? Very simple. EA dash is equal to 160 kilojoules per mole. So this is how we can actually solve the questions and understood, I hope, about the activation energy. Now tell me, what is the final conclusion? Whether either exothermic or endothermic, let us always know one thing. The additional amount of energy that must be gained by the reactant to attain threshold energy is called activation energy of the forward reaction. The additional amount of energy that must be gained by the products to attain threshold energy is called the activation energy of backward reaction. The question is, what is threshold energy? Threshold energy, the minimum amount of energy that must be there, that must be attained by either the reactant or the product to actually make the chemical reaction to occur, that is to convert a reactant to product or a product to reactant, is nothing but called threshold energy. All these things become much more clear in a theory called collision theory. But I wanted you to understand a very important concept called activation energy, which I took. Now it will be easy for me actually to talk about factors influencing rate of reaction. What is the first factor which influences rate of reaction? Nature of reactants. As I already told you, certain reactions are fast, certain are very slow, certain are moderately slow. What does it mean? Any reaction in which number of bonds to be broken and number of bonds to be formed are less, then the rate of reaction will be more. In other words, if the energy of the reactants is already more, the energy that they must gain will be less. Therefore, their activation energy is less. Lesser the bond rearrangements, lesser the activation energy, faster will be the rate. A reaction which involves less number of bond cleavages, less number of bond formations will require less energy to attain threshold energy, and the reaction becomes faster. Mean to say, why are ionic reactions instantaneous or fast? Almost no bond rearrangements that are there occurring in ionic reactions. Almost no bond is being broken, no bond is being formed. Since no bond is broken or formed, they are very fast. Why are molecular reactions very slow? Molecular reactions are very slow because they involve bond rearrangements. Then the question is how and how. Suppose I wanted to do a reaction of, make a reaction of, to give this, and I wanted to perform another reaction. This goes faster. The reason, the number of bond rearrangements are less. In other words, activation energy of this reaction is lesser than activation energy of the CO plus O2 reaction. So, lesser bond rearrangements, lesser activation energy, faster the rate. And that is the reason why I used the word called activation energy. Then the next point comes, what is the other factor which is very, very important to be noted? The other factor that is importantly noted is the temperature. What happens when temperature is increased? Whenever temperature is increased, naturally kinetic energy of the gas molecules will increase. Greater the temperature, greater the kinetic energy. Greater the kinetic energy, greater are the molecules colliding with each other. We are learning an important aspect in chemistry later, that greater are the collisions occurring between the reactant molecules, faster will be the rate. Exactly what will be collision theory we will learn later, but collision frequency plays a vital role. According to the important concept called collision theory, collisions between the reactant molecules lead to the product formation. Thus, when temperature increases, collision frequency increases, rate increases. What is the reason that temperature increase leads to increase in rate? Reason number one, temperature increases, collision frequency increases, hence rate increases. Second reason, number of activated molecules increases. Question now comes, sir, what is the meaning of activated molecules? What is the meaning of activated molecules? The meaning of activated molecules, many molecules can be there. All the molecules will not possess sufficient amount of energy, so that their collision can give product. Only those molecules whose collision contains certain minimum amount of energy called threshold energy, that only can actually give a product. Means a collision occurring between reacting molecules with certain minimum amount of energy called threshold energy only can give products. Such molecules having their energy equivalent to that required minimum energy or more than that are called activated molecules. By giving temperature, you can always increase the fraction of activated molecules, hence rate increases. Thus, two things happen when temperature increases. More number of collisions per unit time will occur. Second, as temperature increases, the more energetic molecules with higher kinetic energy will increase. Hence, also is another reason why their collisions actually give more amount of products. To know what is the effect of temperature on rate of reaction, it has been studied by Mr. Arrhenius. He identified that for every 10 degrees rise in temperature, for every 10 degrees rise in temperature, the rate of a reaction either doubles, in certain cases triples. So, for every 10 degrees rise in temperature, rate becomes double, is nothing but called temperature coefficient. To understand temperature coefficient, what is Arrhenius equation, we will try to see. According to Arrhenius, rate constant K is equal to A into e to the power minus EA by RT. Let me be very clear in each one of them. This is called rate constant. What is rate constant, we will see later, which is actually a measure of rate. And then a pre-exponential factor called Arrhenius factor. And this is actually a very important thing. Fraction of molecules whose energy is greater than EA, greater than activation energy. What is e to the power minus EA by RT? Fraction of molecules whose energy is greater than EA. What is capital A? A pre-exponential factor called Arrhenius factor. What is K? Called rate constant. You can see very clearly when temperature increases, rate constant increases and rate increases because there is a negative sign and the change is exponential change. So, rate and rate constant exponentially increase with increase in temperature. To write the same thing in a logarithmic form, if we take natural logarithm ln k and then you take ln a minus EA by R into 1 by t, if you take this on y axis and if you take this on x axis, this will be the slope, this will be the intercept, y intercept. Therefore, if you see a graph of ln k versus 1 by t, it will be like this, where the slope is equal to minus EA by R and the intercept is equal to ln A. Then the question comes, if the same is written in natural logarithms, how to write it? It will become log k is equal to log A minus EA by 2.303 R into 1 by t. This will be the slope, this will be the intercept. Instead of ln A, log A, instead of minus EA by R, it will be minus EA by 2.303 R. You can very clearly see log K is proportional to minus EA. Greater the activation energy, lesser the rate constant, lesser the rate. But if the same reaction is carried out at two different temperatures, how to write it? Let us say log K1 is equal to log A minus EA by 2.303 RT1. K1 is the rate constant at temperature T1. Log K2 is equal to log A minus EA by 2.303 RT2. Then log K2 by K1 comes out to be EA by 2.303 R into 1 by T1 minus 1 by T2. So, two types of expressions are there. You can see here log K2 by K1 directly proportional to EA. Log K is proportional to minus EA. Log K2 by K1 is proportional to EA. Effect of temperature on a rate of reaction is more when activation energy is more. Rate of reaction or rate constant of the reaction will be less when activation energy is more. If greater activation energy, lesser rate constant. The increase in rate constant is more when activation energy is more. This K2 by K1, can be called as a temperature coefficient when the difference in the temperature is 10 degrees. I am writing the same K2 by K1, but this time the temperature difference is 10 degrees. This ratio of rate constants differing by 10 degrees is nothing but called temperature coefficient, which is equivalent to 2R3 is what has been identified by Mr. Arrhenius. Hope you understood the effect of temperature here. Also, if you wanted to see the graphical representation of the temperature, suppose if you take kinetic energy, better take N by N naught. What is N by N naught? Fraction of molecules is called N by N naught. Of the total molecules N naught, N are certain molecules. This is called fraction of molecules. Fraction of molecules with kinetic energy, if you write, the graph will be like this. What is this? This is, let us say, at a temperature T1. At a particular temperature, you can see fraction of molecules with lesser kinetic energy are less, larger kinetic energy are also less. I will make it a little more better. Now I think this is at a lower temperature T1, this is at a higher temperature. If you can see very clearly, is this not the fraction of molecules with high kinetic energy? These are the fraction of molecules with low kinetic energy, fraction of molecules with medium or intermediate kinetic energy. These are the molecules with high kinetic energy. Here if you see, I will take a different pen to understand this. I am coming back to normal. Now you see the flatter curve is T2, T2 greater than T1. Now tell me, at T1 the curve is steep, at T2 it is flat, and you can see very clearly this is called most probable kinetic energy. The kinetic energy possessed by maximum number of molecules. You can see very clearly the curve with red lines actually is the fraction of molecules with high kinetic energy. Compared to T1, in T2, the fraction of molecules with higher kinetic energy are more. That is the reason why greater number of molecules with higher kinetic energy means greater are the molecules which are activated, greater are the molecules whose collision can give product is there. Hence, as temperature increases, rate increases is also proved by this particular graph. I repeat once again, in T1 the yellow lines actually indicate the T1, the red lines actually indicates the extra energy. So therefore, you can see very clearly the area under the curve at a higher temperature T2 has more number of molecules or fraction of molecules with higher kinetic energy. Therefore, as temperature increases, rate always increases and rate of a reaction increases because activated molecules will be more at higher temperature than at lower temperature. Then what is another factor which influences is a catalyst. What a catalyst does is very simple. Suppose if you wanted a reaction to proceed, potential energy versus reaction coordinates. Suppose this is the graph that you wanted to go with. This is the graph. This is the uncatalyzed reaction. This is the threshold energy. This is, suppose I am drawing a dotted one. What is this dotted one? Dotted is catalyzed reaction, thick is uncatalyzed reaction. You can see this is the energy that must be gained by the reactant molecule to form products in catalyzed reaction. Whereas in the case of uncatalyzed reaction, the energy is only EA dash. This is the activation energy for uncatalyzed reaction. This is the activation energy for catalyzed reaction. EA is greater than EA dash. Therefore, activation energy for uncatalyzed reaction is more than activation energy for the catalyzed reaction. That is the reason why by decreasing the activation energy, the reaction is made fast by a catalyst. So the most important role of a catalyst is to increase the rate of a reaction by decreasing the activation energy. You can very clearly see a catalyst does not change the energy of the reactant, does not change the energy of the product, does not change delta H of the reaction, does not change any other aspect. The only thing that it actually changes is the path. A catalyst takes the same reaction through a path of lower activation energy and makes it to occur faster. Other than that, catalyst does not influence delta H value of the reaction, reactant's energy or product's energy. Thus, temperature increases the rate of reaction by increasing the number of activated molecules. Catalyst increases the rate of reaction by decreasing the activation energy. Suppose, what are the other factors? One factor that we discussed is nature of reactants. Other factor is temperature. Third factor actually is a catalyst. Sometimes in certain photochemical reactions, greater the intensity of light, faster will be the reaction. In certain other heterogeneous catalysis reactions, whatsoever is the concentration of the reactant, sometimes the rate may not be influenced. Surface area of the catalyst plays a vital role. All these things play a vital role. And another important aspect, in general, greater the concentration of the reactant molecule, faster the rate also. Sir, why is that a concentrated solution or always gives a better rate? Concentration is more means number of molecules per unit volume are more. Number of molecules per unit volume are more means number of collisions per unit volume are more. Number of collisions per unit volume are more means number of activated molecules colliding with each other also will be more, hence rate will be more. How does a concentration influence the rate of a reaction is the next one called law of mass action and applying it to an experimental data. Before I go to order of a reaction, I wanted to tell a few important things. Even though Arrhenius has given a beautiful illustration of temperature influence on rate of reaction, it is actually having its own limitations. To overcome this, a theory has been proposed called collision theory. Generally, a collision theory is a bimolecular collision theory. This theory assumes that at a time, two molecules of the reactants will collide with each other. According to this theory, the molecules of the reactants or reactant molecules are hard spheres. It may be one of the important aspects of this reaction. Later on it has been thought to be a drawback also. Why? Because this theory does not actually consider any structural aspects. Only assumes that the collision between the reactant molecules give product. What does this theory say is very simple. In order to make a reaction to occur, it is a must that two molecules must collide with each other. Collision between the reactant molecules is a must. But at the same time, do all the collisions give product? No, it says that only certain collisions in which the reactant molecules possess certain minimum amount of energy called threshold energy can give product. What if the other type of molecules collide? Even though they collide, they don't give product. Suppose if I take a molecule A, which is an ordinary molecule, another molecule called A star. A is a molecule whose energy is lesser than threshold energy. A star is the molecule whose energy is greater than or equal to threshold energy. A plus A, no reaction. A plus A star also no reaction. Also no reaction. But A star plus A star gives reaction. Such a collision which involves two activated molecules only is called a fruitful collision, activated collision or effective collision. Such a collision always gives products. So, in spite of having innumerable number of collisions, only this type of collisions will give product is what is the greatest essence of collision theory. To increase these activated molecules, we use temperature as we already discussed. So, this particular equation also has given, particular theory also has given an equation called rate is equal to Z into e to the power minus Ea by RT. Instead of K, this theory used rate, where Z is called collision frequency. So, many people said that is this a perfect equation? Initially they said yes, it is perfect, but this particular equation failed for complex reactions. It came out to be perfect only for simple reactions. Then they thought, what is the reason? The reason is you have taken a collision frequency indicating that all collisions will give product, but just now we saw that all collisions cannot give product. So, therefore, they have modified the rate equation such a way that they made it as Pz. They added, what is that P? Steric factor, orientation factor. Properly oriented activated molecules, when they collide with each other only, can give product. Thus, what is the greatness of collision theory? It says that when a collision between the reactant molecule gives a product, there are two conditions are to be satisfied. They must not only possess a certain minimum amount of energy called threshold energy, but they should be properly oriented, and a properly oriented collision only can give product. Improperly oriented collision cannot give product. Proper orientation of the collision, you generally study this in organic chemistry under the heading SN2 mechanism. If you see there in SN2 mechanism, in alkyl halide, halide is the leaving group, nucleophile is the attacking group. Nucleophile is electron rich, halide is also electron rich. So, whenever nucleophile wanted to attack the alkyl halide, it cannot come from the same side of halide ion, because both being electron rich repel each other. Hence, halide ion prefers to come and attack from back side, not from the same side of the halide ion. Such a properly oriented collision of the attack of the nucleophile from the back side of the alkyl halide to give a proper product is called properly oriented collision. That gives a better yield of the product, but not from the same side. Thus, never be under impression that just having sufficient energy gives the reaction, but also proper orientation plays a vital role. The only drawback of collision theory, as already told by me, is that it never considers the structural aspects of the reactant molecules, only considers them to be hard spheres. Then comes a very important part of this particular chapter. What is that important part of the chapter? What is order, what is molecularity, what is mechanism? If you recollect, we studied in chemical equilibrium chapter that rate is directly proportional to concentration to the power n. If you see A plus B gives products, then we studied rate is proportional to A concentration into B concentration is equal to K into A into B. If you recollect, this was studied by us in chemical equilibrium chapter under the name law of mass action. Now we are actually applying this law of mass action for certain experimental data. To understand this concept, let me be very clear about a few important things. Do you think that every reaction occurs in single step? No. Very rarely reaction occurs in single step. Reactions which occur in single step are called elementary reactions. What is an elementary reaction? Reaction occurring in single step. But most of the reactions in chemistry are not elementary reactions, they are complex reactions. In a complex reaction, we have many steps. The proper sequence of the various steps occurring in a complex reaction is called mechanism. In this mechanism, you write various steps in a proper sequence. Each step involves certain molecules participating. The number of molecules or atoms or ions that participate in each step of that particular mechanism is called molecularity. Tell me what is molecularity? Every step of a reaction involves the participation of certain molecules or atoms. That number of atoms or molecules that participate in each step of a reaction is called molecularity. Molecularity can never be a fraction, it is always a whole number. Then the question is, what exactly is the important thing in this particular mechanism? The slowest step is the most important one. What is the reason that the slowest step is the most important one? For a given reaction, if there are 3 steps, of the 3 steps, one will be the slowest of all. All may be fast, among them the slowest. All may be slow, among them the slowest is important. Why? First step is completed quickly, third step is completed quickly. But first and third are completed quickly. You cannot go to third without completing second if second is very slow. If any one of the step is very slow, overall process will be slow. So the total rate, the actual rate of the reaction always depends on that step. Hence that step is the slowest step called rate limiting step or rate determining step. In that rate limiting step or rate determining step, how many molecules are participating is called order. So now tell me, the sequence of various steps occurring during a chemical reaction is called mechanism. The number of molecules or atoms participating in each step is called molecularity. The molecularity of the slowest step or rate limiting step is called order. For a given reaction, there can be only one rate limiting step. Hence, when you say molecularity, it is not for the entire reaction. Molecularity is only for each step of a reaction. Order is for a particular step of a reaction, but that step is only one in the reaction. Therefore, molecularity of the slowest step is called order. There can be only one slowest step in the reaction. Therefore, order is for the overall reaction. Molecularity is always for each step. If anybody is asking, what is the molecularity of a complex reaction? It's a ridiculous and stupid question to ask that type, because that has no meaning in it. Why? Because each step has certain molecules participating. So, you should always ask what is the molecularity of the step of the reaction. If they ask what is order of a reaction, yeah, true, because an order can be for only a single step, which is the slowest of all. So, for overall reaction you can have order. So, molecularity is for each step, order is for the overall. Now, tell me how to write both of them. Molecularity, order. This is for each step of a reaction. This is for overall reaction. This is always a whole number, the molecularity. This can be a fraction also, or sometimes can be negative also. Molecularity is deduced from reaction mechanism. Order also can be deduced from reaction mechanism or experimentally determined. Therefore, whether it is molecularity or order, it is always important actually for us to study the reaction in a perfect possible way. To understand this particular point, we will try to see this. Suppose if A gives product is a elementary reaction. What does the word called elementary reaction means? Single step reaction. So, how many molecules are participating here? 1. So, the molecularity of the reaction is also 1. Order is also 1, because this is the only step of the reaction. Molecularity is 1, and molecularity of the slowest step is nothing but called order. So, for this order 1, molecularity 1. Then 2A plus B gives products. 2A plus B gives product is a complex reaction. Then they ask, what is molecularity? What is order? Neither can I tell this, nor I can tell this. The reason, it is a complex reaction. That complex reaction would have involved many steps. In each step, how many molecules have participated is molecularity. So, since I do not know the steps, I cannot tell molecularity. Of this complex reaction, what is the slowest step? In that slowest step, how many molecules have participated also, I do not know. Therefore, I cannot tell what is molecularity, I cannot tell about order. So, what is the important thing to be noted here? It is a must that experimental study must be done for a particular reaction to know what exactly is the order and molecularity of a reaction. For example, if I say A plus B gives products, and I say concentration of A is kept constant and concentration of B is tripled, rate increased by 9 times is one information. And in the same question, concentration of B is kept constant, concentration of A is doubled, then rate increased by 2 times. This is actually a very important and simple type of a question where experimental data is given. What is order will be understood perfectly with this. Let me be very clear. With a common sense, many people are telling that order is something, 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 something. They say write rate equation. In that rate law, you will have some powers to the concentration. They write rate law equation, rate is equal to k into c to the power n. This n is called order. First, how do you write this? For which we require experimental data. This n is called order. How to know that n? For which we require this experimental data. What is the order means? Let me be very clear. Suppose I have a reactant A. If the reactants A concentration is doubled, rate is doubled. Suppose doubling the concentration, rate doubled. Oh, the order is 1. I have doubled the concentration of reactant, rate got quadrupled. Oh, concentration of the reactant has a double influence on rate. Oh, order is 2. I have doubled the concentration of the reactant, but rate remained constant. The concentration of the reactant after being changed also has no influence on the rate. What is its influence on the rate? 0. Oh, it is a 0 order reaction. That is actually the correct chemistry. But to know it mathematically is what we are seeing here. You see, A is kept constant. What is the reason that I keep A constant? By keeping A constant, I am only knowing the influence of B on rate, so that I can tell how does B influence rate. So now tell me, order with respect to B. As you know, rate is always proportional to C to the power n. How many times the rate has been tripled? 3 times. So 3 to the power y. Y is the order with respect to 3. Y is that 3 tripled y. And then proportional to rate. What happened to rate? 9 times. So instead of that proportionality, I put equivalent, equal to. How many times the concentration? 3. Y is, let us say, the order with respect to B is equal to rate how many times? 9. Rate is proportional to C to the power n. C to the power n is equal to rate is equal to 3 square. Y is equal to 2. This 2 is called order with respect to B. Means by tripling the concentration of B, you are making the rate to increase by 9 times. It has a square influence, double influence on the rate. Now coming to with respect to A order. Now what is the concentration increase? Double, 2 power x. Let us say x is the order with respect to. Then what happened to rate? Become 2. So x is equal to 1. Okay. So I have order with respect to A to be 1, order with respect to B be 2. Now what you write? Now whatever that I am writing rate, this rate is experimentally determined by me by using the information given to me, is equal to k into A to the power 1, B to the power 2. This is called rate law, which I cannot write without knowing the experimental data. What is rate law? A mathematical equation which shows the influence of concentration changes of the reactants on the rate equation. In this rate law, whatever are the powers that are there for the reactant molecules, the sum of them is called as the order. What is order? Order is the sum of the powers of the concentration terms present in rate law. What is rate law? A mathematical expression that has been obtained by studying the experimental data, which shows the influence of concentration changes of the reactants on rate of the reaction. Therefore, just like that, writing the coefficients as a power is not going to give you rate law. in order to know the rate law, it is a must that you should have an experimental data which shows the influence of each of the reactants on the rate of the reaction. To understand that, let us say someone just gave 2A plus B gives products and just asked what is rate. They did not give you anything. So, rate is equal to K into A to the power 2B. Can be right or wrong, we do not know. Why? They did not mention whether the reaction is elementary or not. Second thing, if it is a complex reaction, we cannot know, because this no experimental data has been given. So, how can I take the coefficient as the power? It is not. Until and unless I know the experimental data and the influence of A on rate and B on rate, I cannot. Thus, suppose if you are writing in an easier way, AA plus BB gives products, rate is equal to K into A to the power M and B to the power N, where M and N may be or may not be A and B, because this M and N are experimentally determined values. This A and B are just the coefficients. The coefficients A and B need not be the powers M and N. Sometimes it may be a coincidence that they may be, and sometimes it may be correct only if it is an elementary reaction. Not always that A is nothing but M, B is nothing but N. It may sometimes be okay, but not always. This M and N are always obtained from experimental data. Hope you understood what is the order of the reaction. Then you may say, sir, order can be negative, order can be fractional. You said how to. Very simple. Suppose products. Suppose someone says concentration of B constant, concentration of A doubled, rate becomes half. Order with respect to A is, now you see what happened to the concentration of A, doubled. So, concentration to the power order 2 to the power x. Then what happened to rate? Half. So, what is x equal to? -1. Is now the order with respect to A -1. What does it mean? It is negative, okay, fine. What does it mean? By increasing the concentration of A, rate is becoming half. Concentration is increasing, rate is decreasing. So, does concentration of A has a positive influence on rate or negative influence on rate? Negative influence. That is the reason why order can be negative. Order can be fractional. Hope you understood, all of you. And also never forget, whenever you talk about order or molecularity, rarely we have order or molecularity exceeding 3. Most of the reactions in chemistry will have their molecularity 2 or 3, generally 1, 2, 3, unimolecular, bimolecular. Termolecular itself is rare. Even order also more than 3 is very rare. And for an elementary reaction, order is same as that of molecularity. Then, what are the two important types of reactions that we study? First order and zero order. What is a zero order reaction? What is a first order reaction? For example, A gives products. I am talking about zero order. Dx by dt is equal to K into A concentration. Throughout this particular chapter, we use these type of terms, which sometimes is given in your textbook. this way. This is initial concentration. This is concentration after time t. X amount reacted in time t. These are the terminologies that we use in the next 15-20 minutes of the class. Now, what is it? Dx by dt is equal to k into A. Dx by dt is equal to k to the power A minus x to the power 0, because it is a zero order reaction. Therefore, dx is equal to k dt. If you simplify all these things, x is equal to kt. So, this is one of the important mathematical expression that you can have for zero order. Rate constant of a zero order reaction is equal to x by t. You can see very clearly dx by dt is equal to k here, means rate constant of a reaction is nothing but equal to rate. Try to recollect the first part that we studied. Throughout this reaction, rate remains constant. A hint for you, rate of the reaction and rate constant of a reaction, if they have the same units, you can blindly follow that it is a zero order reaction. What are the units of it? Mole, mole, liter inverse, time inverse. You can see these are the units of rate only. Wherever the rate constant of zero order reaction has the same units as that of rate, then you can say this. Then the next question, what is half-life? What is half-life? What is half-life? Generally, English itself is telling the time taken for half of the chemical reaction to get completed. At when T is equal to T half, then x is equal to A by 2. What is A? Initial concentration. What is x? Amount reacted. When time is T half and half of the time is over, initially it was A, when half of the reaction is over, A by 2. So, I can substitute x is equal to A by 2. So, I am substituting here. So, what is happening? A by 2 is equal to k T half. T half is equal to A by 2k. Okay. For a zero order reaction, T half is equal to A by 2k. T half is directly proportional to initial concentration, inversely proportional to rate constant. So, shall we see some graphical representations in zero order? Yeah. X is equal to kt. A minus of A minus x is equal to kt. A minus x is equal to A minus kt, or RT is equal to R naught minus kt. Therefore, if you draw a graph of RT versus T, you will get this one where the intercept is R naught and the slope actually comes out to be minus k. This is another one. Suppose I take T half is equal to A by 2k. So, T half versus A, it will be a straight line where slope is equal to 1 by 2k. Agree? I will go with the numericals only after I complete first order within the next 5 minutes. These are the things. What are the examples of zero order? Suppose there is one reaction called this one, decomposing on platinum at high pressure and 1173 Kelvin, giving N2 plus 3H2, or similarly a 2Hi gas with gold at high pressure, if it gives H2 plus I2. These are two very popular examples of zero order. Decomposition of a gaseous species on a metal surface at high pressure is an example of zero order, because why at high pressure only? The gaseous species get adsorbed on the surface. When the pressure is high, almost all the surface will be covered by the gaseous species. Then what happens? Even if you increase the concentration of the gaseous species like an ammonia or HI, there is no surface available for these ammonia molecules or HI molecules to get further adsorbed. Already the entire surface is covered by the reactant molecules. Further increase in the concentration does not have any influence on its decomposition. A reaction in which concentration changes of the reactant does not influence the rate of a reaction is called as a zero order reaction. At high pressure, the concentration changes of ammonia or HI does not influence the rate, because the entire surface is covered with the reactant molecules. Changes in the concentration does not influence the rate, hence they are considered to be zero order reactions. A photochemical reaction also is considered to be a zero order reaction, because in a photochemical reaction, reactants concentration is not important, but intensity of light is more important. So this is about zero order. Coming to first order. So some important expressions to calculate the rate constant of first order reaction are given to you. Rate is equal to K into A minus X. If you write it the exponential form, this is the case. K is equal to 1 by 2 ln initial concentration by concentration after time t. If you write natural logarithm, this is the case. Now tell me, what are the units of K? Rate constant of a first order reaction has a units time inverse. So time inverse is the very important point to be remembered here. So how does units of rate constant are important in solving the numericals? I will tell you. If you see the next one, K is equal to 1 by T ln A by A minus X, when T is equal to T half, X is equal to A by 2, half life. So, K is equal to 1 by T half into ln A by A minus A by 2, T half is equal to ln 2 by K, which can be written as T half is equal to 2.303 log 2 by K, which can be written as T half is equal to 0.693 by K, where you can very clearly see, if you recollect our 0 order, T half is equal to A by 2K. What is the difference between 0 order rate constant and first order rate constant? In a first order rate constant T half is independent of initial concentration. Here T half is directly proportional to initial concentration. All these things are very important hints. In a particular reaction, if they say it is a first order, whether you start with 10 molar or 2 molar or 5 molar or 8 molar, the T half of that particular reaction does not vary because it is a first order. That is the reason why if at all you take 100 molecules, they become 50 in a particular time. That 50 will become 25 in the same time. Then you can say, oh, 100 to 50 and 50 to 25 and 25 to 12.5. The time taken for each one of these steps, 100 to 25, 10 minutes. 25 to 12.5, 10 minutes. 12.5 to 6.25, 10 minutes. Oh, this is a first order reaction. Because half-life of the reaction is always independent of initial concentration. Instead, 100 to 50, 10 minutes, 50 to 25, 5 minutes. Oh, 100 to 50, 10 minutes, 50 to 25, 5 minutes. Oh, when the initial concentration is becoming half, half-life is also becoming half. Oh, it is a 0 order. Like that, T half plays a vital role. That also we will see in the form of numericals. Then coming to the graphical representations. If you see Kt is equal to K is equal to 2.303 by K by T Now, logarithm of A by A minus x is equal to K T by 2.303. If you take this on y axis, this as x axis, this will become m. So, it will be a straight line passing through origin. I am not telling here this is y axis, this is x axis. Instead, logarithm of A minus x is equal to kt by 2.303. Logarithm of A minus x is equal to log A minus k by 2.303 t. Now, this is taken on y axis, this is taken on x axis, this will be the slope, this will be the intercept. So, you will have this as the graph when log A minus x will be there with t, where the negative slope is equal to minus k by 2.303 and the intercept will be log A. Suppose if you have T half is equal to 0.693 by K, if you take T half versus A, it will be a straight line which is parallel to A, because initial concentration does not influence the rate of T half of a reaction. These are all some important mathematical expressions for the rate constant of a first order reaction. Always never forget, 1 becomes a half, half becomes 1 by 4, 1 by 4 becomes 1 by 8, 1 by 8 becomes 1 by 16. 1 to half to become 1 by 4, 1 by 8, 1 by 16, 1 by 32. 1, 1 by 2, 1 by 2 square, 1 by 2 cube, 1 by 2 power 4, 1 by 2 power 5. This 2, this 3, this 4 and this 5 always are called the number of half-lives. I mean to say 1 to half to 1 by 4 to 1 by 8 to 1 by 16 to 1 by 32. This will be t half, this will be another 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 t half. I mean to say, if anybody is asking you if t half is equal to 50 minutes for first order, then time taken for 87.5% of reaction is very simple. First, 87.5% is nothing but 7 by 8. 7 by 8 is 7 by 2 cube. This power 3 will tell you half-life. 3t half is how much is asking? 3 into 50, which is equal to 150. No sir, I wanted to get it in a different way. No problem. T 87.5 by T 50 will be logarithm of 100 by 12.5 by logarithm of 100 by 50. So how did we get this question? 2.303 by k I cancelled. Now this will be equivalent to logarithm of 8 by logarithm of 2, which will be 3 log 2 by log 2, which will be cancelled. Also you can get that log 87.5 by log 50 is equal to 3. This is also the way in which you can do. So whenever you are given any fraction, always the fraction will be 2 power 1 or 2 power 2 in the denominator, 2 power 3 or 2 power 4 in the denominator. The power that is there for the 2 always indicates the number of half-lives. If anybody is asking any type of a question, relate T 99.9% to T 50% of first order. Absolutely no problem. T 99.9 by T 50 is equal to logarithm of 2.303 by k cancelled. 100 by 0.1 by logarithm of 100 by 50, which is equal to 3 log 10 by 0.3, which is equal to approximately equal to 10. So T 99% to T 50 is approximately 10. T 99.9% is 10 times 3 T 50% of a reaction. Can we do these type of reactions for zero order? Absolutely. What is zero order? Kx is equal to kt. T 75% to T 50% for zero order they are asking. What is 75%? 75% of the reaction is over. Here 50%. So x is equal to 75 in one case, x is equal to 50 in the other case. Therefore, T 75 by T 50 happily will be 3 by 2. Why? Because x is equal to kt, T 75, T 50, x is equal to kt, T 75% is equal to k into t, x is 75, x is, so if you wanted to show it in a different way, T 75% is equal to x by T75% is equal to 75 by K. T50% is equal to 50 by K because K does not change. So, T75 by T50 is equal to 75 by 50, which is 3 by 2, which is not an issue at all. So, whatever is the case, rate constant depends only on two things, Andy. Rate constant depends on temperature, rate constant depends only on catalyst. Concentration changes do not influence rate constant. Suppose someone is giving you A gives products. Initially I took 8 molar of A. After 40 minutes, concentration of A is 2 molar. K is dash for a first order reaction. Very good. A is equal to 8 molar. A minus X is equal to 2 molar. K is equal to 2.303 by T, which is 40, logarithm of 8 by 2, 2.303 by 40, log 4, which is 2 log 2. Therefore, 220 is a 0.3010 by 20. Simplify it. For a reaction, 2A gives product K is equal to 10 second inverse. Order is, how to know this? The most important thing is time inverse. Therefore, order is equal to 1, because the time inverse actually is nothing but for order of a first order. Rate units of first order reaction are time inverse. Therefore, you can get the order as 1 because of the time. So, is there any technique? Yeah. General units of K, mole liter inverse to the power 1 minus n time inverse. N is equal to 0, mole liter inverse time inverse. N is equal to 1, substitute there, time inverse. N is equal to 2, liter mole inverse time inverse. Like that you can tell about each order by looking at the units of K. You can see units of K are nothing but units of rate here. Units of K are time inverse. Units of K are liter per mole. So, by looking at the units also you can say. So, it is a very important relation for you. Here also I did the same. Here it is time inverse. Time inverse is for first order. Therefore, I wrote first order. Similarly, T half is proportional to A to the power 1 minus n. If n is equal to 0, T half is proportional to A. If n is equal to 1, T half is independent of A. If n is equal to 2, T half is proportional to 1 by A. You can very clearly see T half is directly proportional to initial concentration for 0 order. T half is independent of A for a first order reaction. T half is inversely proportional to A for a second order reaction. Suppose if anybody says 1 molar is A, then T half is equal to 10 minutes. A now becomes, let us say, 2 molar, T half is equal to 20 minutes, then you can say that order is equal to 0. How? When the initial concentration has doubled, then the T half also doubled. So, T half directly proportional to A. Instead, A is equal to 1 molar and A is equal to 10 molar. T half initially is 5 minutes, now also it is still 5 minutes. Then what is order? Oh, order is equal to 1. How did you do that? When I changed the initial concentration, T half did not change. Influence of initial concentration is not there on the half-life of the reaction, therefore it is a first order reaction. A is equal to 10 molar, A is equal to 20 molar, T half is equal to 10 minutes, T half is equal to 5 minutes. What is order? Order is equal to 2. Why? When I doubled the initial concentration, T half has become half. So, T half is inversely proportional to 1 by A, order is 2. This is how we can do some simple numericals that are present in the reaction. For example, suppose someone says A gas gives B gas plus C gas is a first order reaction. Initial pressure of it is 100 mm. After 10 minutes, the pressure is 150 mm. K is equal to how much? So, first let us go. A gives B plus C. Pi is equal to 100 dash dash. P after time t is equal to 100 minus P given 100 minus P plus P is equal to 150, P is equal to 50. Therefore, K is equal to 2.303 by how many minutes? 10 minutes logarithm initial 100 after time something is 50. Therefore, 2.303 by 10 log 2 0.693 by 10, which is 0.0693 minute inverse. 100 is the initial pressure. After 10 minutes it is 150. 100 minus P, for 1 mole 1 is formed P, for 1 mole 1 is formed P. So, therefore, 100 minus P plus P plus P is 150, 100 plus P is 150, P is equal to 50, I substituted 100, 100 minus 50 and I calculated and I got the answer. Hope you understood that. Now, suppose someone says rate constant of a reaction is 10 to the power minus 2 mole liter inverse time inverse. Rate of reaction of 1 molar reactant at that time is, oh, he gave you rate constant, he is asking you rate. Rate is equal to rate constant into a minus x to the power n. Rate he wanted, rate constant is 10 to the power minus 2, a minus x to the power 0. Sir, why did you put a minus x to the power 0? The units are playing a vital role here. because the units actually indicate that it is a zero order is the most important point. I have put it. So, rate is equal to 10 to the power minus 2 mole liter inverse time inverse. Suppose if they gave you question as rate of a reaction is dash if rate constant is 2 into 10 to the power minus 1 minute inverse for a 0.5 molar A gives product is the reaction. Rate of a reaction A gives product is dash if the rate constant is this much and concentration of A is at the time is 0.5. Once again, how to proceed? Order is equal to 1. How did I get order is equal to 1? The units are meter inverse. So, therefore, rate is equal to 2 into 10 to the power minus 1 rate constant into 0.5 to the power 1. Rate is equal to K into concentration to the power 1. So, it will be 10 to the power minus 1 mole liter minute inverse. You can do as many numericals as you want. So, these are the important aspects of this particular chapter called chemical kinetics. So, we can do many more such questions. Thank you very much. That's all in chemical kinetics. Thank you.